What's up, guys? We're starting Intro to Derivatives. This is pre-calculus, but honestly, this is calculus. We're going to start down a very fun and wonderful world of calculus with this unit. And the very first lesson here is the tangent line problem. This is the problem that's going to get us into calculus. So before we dive too much into what the tangent line problem is, let's first talk a little bit about calculus. Calculus is all about understanding change. Calculus is a branch of mathematics that helps us understand changes between values that are related by a function. Many of these formulas are functions of time, and one way to think of calculus is to see it as a study of functions of time. In this unit, we will focus almost entirely on the rate of change of a function. So how much is the function changing, and at what rate is it changing over time, typically? So let's look at a function real quick so we can kind of understand what I'm talking about when we talk about changing. So here is a function, just a random function. We'll just call it f of x. And we notice that, as we start, and we always view graphs left to right. So as we start here, and as we start to travel to the next point, and then to the next point, and to the next point, there's millions of points. But every time we change from point to point, the function changes, right? For example, as I change from point 1 to point 2 to point 3, you might notice that the function value is getting lower. That's one thing we notice about how it's changing. And then it keeps changing, it keeps getting lower and lower, and then it starts to go back up and increase as we continue to go. So we see that the points are changing. Being able to measure, understand, and express how a function changes over time is super important, a very big, huge part of calculus. So let's dive into a couple different ways that we could talk about the rate of change of a function. So first, let's talk about the average rate of change between 2 points. We've actually done this a while ago, but we're going to really kind of make sure we understand it today. So we're looking at the average rate of change between a point, x comma f of x, and a second point, which is a horizontal distance of h away. Now that's a little bit confusing, so let me explain. So we're going to first start off with any point on the function, and I'm going to start off with this blue point. Let's call it point P. And that blue point has an x value of a, just any value, and its y value would be f of a. That's pretty simple. So I'll give you the x value. To get the y value, you plug it into the function, hence f of a. But if we take that value and we slide over, so we take that a value, whatever it is, and we move over a distance of h. So again, we're going to slide over a distance of h. So we're going to stop, and that new stopping place would be a plus h. It was just that a value slid over h units. So hence now it's a plus h. So this provides us a second point. We'll just call it q. And that coordinates of that second point is a plus h, right? It's just that a value slid over whatever h is, comma f of a plus h. Once again, how do you find the y coordinate? You take your x coordinate and plug it into the function. So now that we have 2 points, a beginning point at a and a second point slid over to a plus h, to find the average rate of change between these 2 points, all you have to simply do is find the slope of the line that contains these 2 points. So it's really, really simple. It's just finding the slope of the line that contains these 2 points. So I drew in this pink line that connects point P and point Q, and the average rate of change from point P to point Q is simply the slope of that line. So how do you find slope? Well, let's go all the way back to algebra 1. First off, we use the letter m to represent slope typically, and back in algebra. And slope is the y coordinate of the second point, f of a plus h, minus the y coordinate of the first point, f of a. So that's my numerator. And then divided by subtracting the x coordinates. So again, that's the x coordinate of the second point, a plus h, minus the x coordinate of the first point. Now, the numerator, again, is the y minus the y, f of a plus h minus f of a. But if you look at the denominator, a plus h minus a, those a's will reduce to a 0. A minus a is 0, and that's why we just have an h in the denominator. And again, remember, slope is vertical distance, vertical change over horizontal change. And the horizontal change was h. We slid from a to a plus h. That's why the horizontal change is essentially just the distance we slid over h. That's the denominator. And then the numerator is, again, that vertical distance from f of a plus h to f of a. So we get a nice little formula here, very simple formula. You guys should know how to find slope. And all we say is that the average rate of change between 2 points is simply the slope of the line that contains those 2 points. Now, we call such a line between 2 points on a function a secant line. Just to kind of connect this does not connect to secant from trigonometry. This is secant actually from circles back in geometry. If you remember, a line that crosses a circle twice is known as a secant line. So that's kind of where we get the name from. So a line that passes through a function at 2 points is called a secant line. So we say the slope of the secant line, we'll put a little SCC there for secant. The slope of the secant line, again, is the y-coordinate of the second point, f of a plus h, minus f of a, that's the y-coordinate of the first point, all divided by h. So it's a really, really simple formula to use. And essentially, you have 2 points, and you're simply finding the slope between them. It's really not more complicated than that. Don't get lost on h. H is simply the distance between the 2 points, which is why the denominator is just h, because it's that horizontal distance that we changed by. Now let's look at a problem where we're actually going to utilize this formula. Really, really simple. So for the function below, find the average rate of change from x equals -1 to x equals 4. So if we're thinking about the function 2x squared minus 3x, we want to find the average rate of change from x equals -1 to x equals 4. So once again, I'm going to write down the formula for this slope. It is f of x plus h. Well, I'm actually going to replace that x with an a. Minus f of a, all divided by h. So now we kind of have to think how this works. So this is actually really simple, but some kids kind of overthink it. So let's see here. A is our beginning point, which is -1. And from -1 to 4, right, to get from -1 to 4, that's a distance of 5. So that's my h value. My h is that value that I moved from -1 to 4 is 5. So that's how I get that. Minus f of a. A is, again, the beginning point, -1. All divided by the distance I traveled, again, from -1 to 4 is a distance of 5. That's the h value. So again, essentially, -1 plus 4, not essentially, -1 plus 4, -1 plus 5 is 4. So we get f of 4 minus f of -1, all divided by 5. Now, some kids that they get a little bit lost in this formula, if you want to think of this as quite simple, right? The first point is -1 comma f of -1. And again, that's the y-coordinate, which, how am I going to get that y-coordinate? I'm just going to plug it in here in one moment. And the second point is 4 comma f of 4. So all I'm doing is finding the slope between these 2 points, which is taking the y-coordinate of the second point, f of 4, right there, minus the y-coordinate of the first point, f of -1, which is right here, and then divided by the distance between the x's. 4 minus -1 is +5. So I'm really just getting 2 points and find the slope in between them. All right, so now I just got to actually get my y values. So f of 4, that's the y value when x equals 4. So I'm just going to do a little bit of dirty work. That's going to be 2 times 4 squared minus 3 times 4. And if you need to do that work on your calculator in your head, that's fine. 4 squared is 16. 2 times 16 is 32. 3 times 4 is 12. So 32 minus 12 is 20. So that's my y-coordinate at f of 4 minus the y-coordinate at -1. So once again, that's 2 times -1 squared minus 3 times -1. So -1 squared is 1. 2 times 1 is 2. -3 times -1 is +3. So 2 plus 3 is 5. So there's my y-coordinate there, all divided by 5. Again, 5 is simply the distance 4 minus -1, the distance between my x's, which again is 5. So 20 minus 5 is 15. 15 divided by 5 is 3. So the average rate of change between these 2 points is 3. So between these 2 points, the slope of the line that connects them is 3. That's the average rate of change between these 2 points. Pretty easy, not too difficult. But now we want to move on to something that is truly brand new, and that is what we are going to call instantaneous rate of change. This is the rate of change at a point not between 2 points. So the slope of the secant line, again, a secant line is a line that connects 2 points of a function. Well, we don't want to talk about 2 points anymore. We want to talk about 1 point. So we want to talk about the slope of the line at this point, right? The rate of change at this point. Rate of change is just, again, a fancy word or fancy phrase for slope. But the problem is if you have like a single point, right, you could run, I mean, a million lines through it. There's a line, 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 there's a line. So that's the problem is how do I find the actual slope at this point? You could kind of draw it approximately right there. It kind of just nicks it right there. That would be the slope. But again, how do you find that slope? Because for years and years and years, we've always been told you need 2 points to find the slope of a line. But we don't have 2 points. We just have 1 point. And again, this is called instantaneous rate of change because it wants to know the slope, the rate of change, at that 1 point. At the one instant where x equals a, what is the rate of change? Not between 2 points, that was what we just covered, at that value. So getting this is where we're going to need some pretty cool math that you guys should already be familiar with. So let's start off with looking at this picture. This is back to that original picture where we were talking about the rate of change, the average rate of change between 2 points. So again, I could kind of draw this line in. That's the secant line that connects these 2 points. But check this out. If I take the second point and move it closer, move it a little bit closer, which means my h value gets smaller, I'm going to draw another secant line. And that secant line it's still a secant line because it's still connecting 2 points, but it's getting closer to that perfect slope at A. So again, let's move it closer. So let's move that second point in closer. Once again, reducing h. And again, make a new secant line. And that secant line it's getting really, really close to the line I'm looking for. So let me draw the line I'm looking for in black here. The line I'm looking for is the line that is tangent, right? It's not, it just touches just one time. So I'm looking for that line that's tangent to x equals a, right? It's that line that only crosses the blue point. It doesn't cross any other point. So that's a tangent line, not a secant line. But here's how we're going to find that line, or the slope of that line. We want to know the rate of change, right? And again, I'm moving this second point closer. I'm reducing my value of h. So again, if I move it a little bit closer, and I draw that line, now that line's getting even closer to the black line. The closer I take my second point to the blue point, the closer and closer my secant line becomes that tangent line. And again, if I get super duper duper close, almost right next to it, notice that the secant line is very, very close to the tangent line. So here is the idea. If we allow h to get smaller and smaller and smaller, if we allow h to approach 0, as h gets closer and closer and closer to 0, now remember h is the distance between my original point and my second point. As that distance gets smaller and smaller and smaller, the slope of the secant line connecting the 2 points will get closer to the slope at the blue dot, at the original point. A little bit confusing to understand, but I hope that you guys get that idea. Again, we'll start off with the secant line connecting 2 dots. We bring the second point closer and closer and closer to our original point. So we're allowing h to approach 0. And as h gets closer and closer to 0, our line gets closer and closer to the tangent line. The instantaneous rate of change at a point is the slope of that tangent line at the point a comma f of a. This can be found exploring the limit of the average rate of change as x approaches 0, or excuse me, as h approaches 0. And it might take a little bit of time for this to really soak in, but again, we're trying to find the slope of the line that is tangent to our 1 point. And to find the slope of that line, we start off by finding the average rate of change between 2 points. And we bring that second point in closer and closer and closer. And as the distance between our 2 points gets closer to 0, basically, if it gets to 0, then I'm at that point. And again, that's the slope I'm looking for. I'm looking for the slope of the line at that one single point, a comma f of a. So I take the average rate of change formula that we've already learned, f of a plus h minus f of a divided by h, and we allow that h value to shrink and shrink and shrink and shrink and shrink, bringing our 2 points closer together. Hence, we'll get closer and closer to the slope of the tangent line. Working these problems is a process, but you must truly understand what it is you are finding with this formula. We're finding the slope of the tangent line at a given point, a comma f of a. If you're looking for one more way to visualize this, here's a second, much nicer picture than mine, but it shows the point P, the original point at x equals a that we want to find the slope of the tangent line. And the tangent line is this line right here that only crosses the function at that point P. But to find that line, what we have to do is think about that second point Q. And anytime we connect 2 points, that's called a secant line. But if we move that second point closer and closer and closer to the original point P, yes, those are all secant lines, but as that point gets closer and closer to point P, the closer and closer the secant line turns into that tangent line. That is why this is really a limit problem, because as we talk about the average rate of change between point P and point Q, but as we allow the distance between those 2 points to shrink and shrink and shrink and shrink and shrink to 0, what we will find is the slope of the tangent line instead of the slope of the secant line. So I really hope at some point after listening to the last couple of minutes that you truly understand what we're trying to find here. And it may take a little bit more time, I get that. But this is what we're doing right now. We're trying to find the slope of that tangent line. It's the instantaneous rate of change. Slope is just a fancy way of saying rate of change, or vice versa, at a point as opposed to between 2 points. And we need limits to be able to do that. All right, let's talk about how to do these problems, because these problems, I love doing these problems. I think at the end of the day you will as well, but they do take some time. So let's walk through the steps. Step 1. Always start with writing the formula and substituting in a. A is going to be the x value that you are told to find the slope at. Step 2 is using the function to evaluate the numerator using the function. Using the function to evaluate the numerator using f of x. The h and the denominator must cancel. So use your algebra skills to make that happen. So we're looking for the h to cancel. And I'll explain a little bit more about that in a second. Step 4 is once the h and the denominator cancels, we're going to use direct substitution by substituting in 0 for all the remaining h's. Let's go back to the formula for 1 second. This is a very generic formula with a being any value. But notice that if we use direct substitution right away, if we plug in 0 for h, this turns into a 0 and this turns into a 0. So in the numerator, we get f of a minus f of a, which is 0. And the denominator, we get 0. Remember, when you get that double 0 when evaluating a limit, there is an answer. The limit does exist, but you're going to have to do some work to find it. And again, that work is to evaluate the numerator using the function, and then find a way to get h to cancel. And then once the h cancels, you're going to go and use direct substitution again. Now, these steps might mean nothing to you until we start taking a look at some problems. But I want you to note that as we work on these problems, that you should be working them exactly how I do. All right, here we go. Here's our very first problem. Find the slope of the tangent line to the graph of f of x squared plus x at the point 2, 6. Now, sometimes it does help to visualize this. So here's a quick look at the graph. And 2, 6 is this point right here. And I want to find the slope of the tangent line that just crosses that function at that one exact point. All right, so the first thing I'm going to do, as I wrote out, was utilize the formula for the limit. So the formula for the slope is the limit as h approaches 0 of f of, now it's a plus h, but I actually know a is my x value 2, so that's going to be 2 plus h, minus f of a, which is 2, all divided by h. So again, that was step 1, substituting in a, which is my x value, 2, into the formula. All right, now I have to utilize the function to evaluate my numerator. Notice how I have to continue to rewrite the limit. If I stop right now, it's 0 over 0. Don't believe me? Plug in 0 for h. You get f of 2 minus f of 2, which is 0, and you get a 0 in the denominator. So we're going to keep going. All right, so I have to plug 2 plus h in to my function. Remember, this is the function that helps me find y values. So I'm going to go ahead and plug in 2 plus h. So that's going to be 2 plus h squared plus 2 plus h minus f of 2. Now, I already know what f of 2 is. That's 6 because I was given the point. But if you want to confirm that, plug 2 into the function. You get 2 squared plus 2. 2 squared is 4. 4 plus 2 is 6. All divided by h. All right. Now I got to continue to use my algebra skills to somehow, some way, get the h in the denominator to cancel. So I'm going to go ahead and actually multiply out the top. 2 plus h squared is 4 plus 4h plus h squared. There's nothing to distribute here, so I can get rid of those parentheses on the 2 plus h minus 6, all divided by h. If you don't understand how I got 2 plus h squared, then go ahead and come to the side and do 2 plus h times 2 plus h, and you'll see exactly how I got it. And now I'm going to go ahead and clean up that numerator a little bit more using my algebra skills. So let's see here. First off, 4 plus 2 is 6. 6 minus the 6 is going to be 0. A 4h and a 1h is a 5h. So I get 5h plus h squared, all divided by h. And I'm thinking, how could I get that h to cancel? Ooh, factoring. If I factor out an h on top, I'm left with 5 plus h, all divided by h. Those h's cancel. Now I'm ready to go. So step 1 was substitution into the formula. Step 2 was cleaning up the numerator using the function. Step 3 was using algebra skills to get the h to cancel. And now I'm ready to find the limit. This is going to get my slope, to find the limit as h approaches 0 of 5 plus h. Now that I got that h to cancel, I could use direct substitution. Replacing h with 0, I get 5 plus 0, which is 5, and that is my final answer. The slope of the tangent line at 2, 6 is 5. So again, going back to this graph, we could clearly see my tangent line is this. I'm going to try to draw it as best I can. It's this line right here. The slope of that blue line that is tangent to 2, 6 is 5. How cool is that? So now that we've found the slope of the tangent line, we can actually find the equation of the tangent line. Remember, we already have our point 2, 6. We now know the slope is 5. So now what we need to do is simply find the equation of the line that contains the point 2, 6 with a slope of 5. I'm going to use point slope form. Y minus the y coordinate of 6 equals 5. That's the slope times x minus the x coordinate of 2. So that's a great answer in point slope form. If you want slope-intercept form, we got to do a little bit more work. We have to distribute the 5x plus, minus 10. Add the 6 over. Y equals 5x minus 4. That is in slope-intercept form. So you got to read the directions to know what form you need to be in. But again, both of these equations represent the equation of that blue line, the tangent line at 2, 6. So this is the rate of change at that point. Not between 2 points, that's a secant line. The tangent line is the slope at that point. All right, now I want you guys to try the next one on your own. So in a second, I'm going to reveal the next problem. Pause the video. I'll give you a moment to pause it. Try to do the problem on your own and see if you get the same answer as me. And then when you hit play, you will see the answers. So here is the question. Find the slope of the tangent line to the graph of f of x equals 2x squared minus 3 at the point negative 3, 15. Go ahead and do that now on your own. And when you come back, it will have the answer revealed. And here's the answer. Step 1, I just substituted in negative 3 for a into the formula. Step 2 was actually using the function to evaluate the numerator. And then I used my algebra skills to reduce the numerator as much as possible. And then I factored out an h. Once those 18s canceled, I factored out an h. And those h's canceled. Now, that's why I changed it to red, to show you the direct substitution, plugging 0 into my new formula, and the 2 times 0 is 0, so I just get a slope of negative 12. So the slope of the tangent line at the point negative 3, 15 is equal to negative 12. Notice that I wrote m the entire time because I was trying to find the slope, and I rewrote the limit every single step until the very end when I actually used direct substitution to plug 0 in for h. That's when I was done writing the limit. Most students like these problems, but a lot of students don't want to do the necessary work because they just get lazy. So please make sure you don't fall into that trap. All right, let's do one more problem together. Find the equation. So this time they don't want me to just find the slope of the equation. But remember, to find an equation, you need the slope. So even though it doesn't say find the slope, it says find the equation, and you can't find the equation without a slope. So find the equation of the tangent line to the function f of x equals x plus 1 at the point 3, 2. I actually graphed this function. Here it is. I graphed it in Desmos. 3, 2 is right here. So you can almost envision the tangent line. Try to draw as best I can. Not very great. But I want to find the equation of that tangent line. All right, so once again, I'm going to start off with my formula for the slope is the limit as h approaches 0. I'm going to substitute in my x value of 3 for a. So that's 3 plus h minus f of 3 all divided by h. Step 2 is using the function to evaluate the numerator. And let's see here. It's going to be the square root of, and I'm plugging 3 plus h into the function. So that's going to be 3 plus h plus 1 minus plugging 3 into the function. 3 plus 1 is 4. Square root of 4 is 2. But again, I already knew the y-coordinate for 3 was 2. All divided by h. Now, once again, if I plug 0 in right now, I'm going to get 0 over 0. That's why I got to keep going and use my algebra skills. Now, what do I do here? Well, remember, we're going to multiply by the conjugate. You may remember, because again, that's why we learned those strategies. So I'm going to take the 3 plus h plus 1 minus 2, all divided by h. I'm going to multiply by the conjugate, which is the square root of 3 plus h plus 1 plus 2, all divided by, again, you got to multiply by the same thing in the denominator, square root of 3 plus h plus 1 plus 2. So again, most kids hate having to rewrite the limit every single time, but sorry, you got to do it. All right, when I multiply the numerators, first off, the square roots cancel, which is awesome. 3 plus h plus 1. The outside and inside terms cancel, which always happens when you multiply conjugates. That's why I love doing it. So the outside 2 times the square root of 3 plus h plus 1, and the inside negative 2 times the square root of 3 plus h plus 1 cancel. And then finally, negative 2 times 2 is negative 4. All divided by, now be very careful, in the denominator I have h times the square root of 3 plus h plus 1 plus 2. Don't ever do anything in that denominator. Now I'm going to come up here and continue on my work, but let's see here. 3 plus 1 is 4. 4 minus 4 is 0. So all that's left in the numerator is h. And the denominator I have h times the square root of 3 plus h plus 1 plus 2. Those h's are going to cancel. And yes, this is awesome. That means I'm ready to go. I'm going to change colors here so we see that. Now I'm going to find the limit as h approaches 0 of 1. H divided by h is 1. Divided by the square root of 3 plus h plus 1 plus 2. So now that I got those h's to cancel, I'm ready to do direct substitution. No longer have to write the limit. I'm just going to substitute a 0 in for h. So 3 plus 0 plus 1 plus 2. 3 plus 0 plus 1 is 4. Square root of 4 is 2. 2 plus 2 is 4. So I get 1/4 as my slope. So the slope of this blue line at the point 3, 2, tangent to the point 3, 2, is 1/4. Now, the only thing left for me to do, because remember the question did say find the equation, so I already have my point 3, 2 that was given to me. I now have my slope of 1/4, and I now just have to find the equation of the line. I always recommend using point slope form. It's the easiest one. Y minus the y coordinate of 2 equals the slope 1/4 times x minus the x coordinate of 3. So there is the equation of that blue tangent line. Now, if it doesn't ask for slope-intercept form, you could just leave it like this in point slope form. If it does ask for slope-intercept form, you would need to distribute the 1/4 and then add the 2 over. But all it said was find an equation. I got an equation. Point slope form is a good equation for a line. So what have we done in this video? We've talked about change. The average rate of change between 2 points, which is really just finding the slope between 2 points. I mean, my goodness, that's Algebra 1 material. And then now the new material, right, the beginning of calculus is finding the slope at a point, finding the rate of change at a point, which involves finding the slope of the tangent line at a point. And that is where we need limits for that, because you can't just find the slope of a point. It's impossible. You cannot find a slope with just one point. That is why we need to use the limit, because it allows us to say, hey, what we're doing when we're using the limit formula is we're bringing that second point closer and closer to closer. And if that second point eventually gets all the way to my one original point, then my secant lines have turned into my tangent line. And now I have found the slope of that tangent line. So please note the process to solving these problems. They do take time, they do take a lot of work, and they do take a lot of rewriting, which most kids don't like to do. But if you want to do well in this unit, you got to be able to do it. All right, see you in the next video. If you have any questions, please let me know.